Yeah, hello. This morning, global economics, and we went through general description of macroeconomic indicators, and then the last time we started to go a bit deeper into detail into time series analysis, and together with you, I want to do a little correlation analysis and least square estimation for the dependence between unemployment and GDP growth. And yeah, for this we talked about the so-called Okun's law, and this was in the beginning purely descriptive observation that, not very surprisingly, that we have a dependence, that the unemployment rate is low, that in general we would have a high GDP growth. But what it was a bit surprising is that this is not only a one-to-one mapping, but that we have a or we found in the United States for the data that a difference in, or the cyclical component of unemployment, a rise of 1% would lower, so to speak, economic growth or the output gap by 2%. So what was descriptively found in the US data was that if we write down here the change or the difference between the actual unemployment rate minus the natural unemployment rate, that a change here will have an impact of a 2 times higher change in the so-called output gap. So Y star is potential output and Y is the actual output. Well, and if we write down this gap version, translating it into the growth version, which we can handle later on a little bit easier, then this would mean that a change of unemployment over time equals the difference between actual GDP growth minus potential GDP growth. And well, in the data of the United States, we found here this factor 2. And what we want to do together is that we take the nowadays data. I will go through this as an example for the United States and for Germany, and then just estimating this parameter with the nowadays data, and of course that we are varying the time period where we look at. Well, and We discussed just the reasons for this dependence, that we do not have a one-to-one mapping, and in general we could say that the firms do not directly adjust their employment. And of course, if we look especially for Germany, then we have an increase of labor participation, that people who formerly worked part-time now increased their time they are working. And of course, that we have increases in labor productivity. That means that today, with the same time of work, we can produce more compared to the past time. And here I showed you the US data from 1949, where we just plotted GDP growth versus the change of unemployment, and for every year since 1949. And in this case, we find, not very surprisingly, this negative dependence. And what we now want to estimate is what would be the best line to fit this data. And then we want to estimate especially this slope of this line, and the slope of this line would be then to be identified with, or we can compare this with the -2. And of course, we won't find exactly a -2, but a different number, and then we can interpret this number and also the cut of the vertical axis here. If we look at the growth version, then we see that the cut of the vertical axis we can just interpret as an estimation for potential growth. Yeah, and well, as I know, you haven't done linear regression within your statistic course, so I want to go through the theory with you, that you learn how to do such a linear regression. Well, and then let's take just a little example, and we think of, yeah, an analysis within a company, and that we would say, well, we are selling our goods in that way that we have some representatives, so people outside my company, and they are going more or less from door to door, try to sell their goods. And then we found in history, when we look into in our data, that if we have made 9 visits, I had a sales volume of 24 euros. And in 2009, I had 11 visits and I had a higher sales volume of 33, and so on over time. Well, and now I can pose the question, well, I more or less see, if I'm looking just at this table, that I can also identify a qualitative dependence, that the more visits, the higher is the sales volume. And now I want to have a quantitative answer from my historical data. Well, if I really potentially increase my visits up to 30 visits, what could I expect using my historical data for the sales volume then? And this is a very interesting question for you in your company, because increase of the visits would in general mean that I hire a new person. Well, and for this, I have to have an idea. If I hire a new person, then I have to pay this person, and the increase of my sales volume, that then enough in order to pay in future a new person. Well, and for this, we think of a general dependence between these two variables. One variable we want to explain, and this would be then the dependent variable. In our case, this would be our sales volume. And the independent variable, these are our visits. So what we want to do is we want to explain one variable, y, sales volume, with our independent variable x, our number of visits. And this would mean that a change of x will imply a change of y. And we think of a linear dependence between these two variables, and we could, for example, assume that it is just a linear line with a vertical cut of 3 and the slope of 2, or in general, we of course do not know directly these two parameters, and then we would have the general linear line y equals a plus bx. So this again is our vertical cut, and here we have our slope. Yeah, but now if we are going to our data, then of course, not for every data point yi, xi, we have the same parameters a and b. So in general, we want to have a, so to speak, best fit, that this is our value we want to estimate for, in our case, x is 30. What would be then our y? And these two coefficients, a and b, we want to calculate from our data set. So in general, let's say we have y and x. Oops. This one. And let's say our data looks like this. Then this is x1, y1, x2, y2, x3, y3, x4, y4. Let's take another color, red. And then, oh, this is blue anyway. Then this would be maybe our regression line. A little bit smaller here. And then, of course, we have a y1 hat, which is lying on the regression line. And here we have the difference to the actual data point y1. So if we are fitting our linear line, then only by accident our data point will directly lie on our regression line. So in general, we will have a difference between the actual data point and this would the value on the regression line. And this then we call our error when we are estimating our regression line. Well, and now what we are doing is that we want to find the best regression line, so an estimation for A and B. And our aim would be that we want to minimize the sum of all errors. So in my example here, I would have 4 errors. So y1 minus y hat 1 plus y2 minus y hat 2 plus y3 minus y hat 3 plus y4 minus y hat 4, always the square. This is sum, and this one we want to minimize. Well, what does it mean to minimize this square? This comes just from what you hopefully have already seen in your statistics course, that you there also defined the difference between the data point and the mean of your sample, that you define this as the variance. So in general, this means to minimize the variance. And now we want just to find the formulas for A and B if we have this formal optimization problem. So in this case, we then have just a function depending on our two parameters we want to estimate, A and B. This is the data, so known data points. This one here, as we have defined it here, are our y data points lying on the regression line. So this is just y I hat. So these are just our squared errors. question, what do we have to do when we have a function depending on two variables and we want to minimize this function? What we have then formally to do? What would you do if you have a function depending only on one variable when you want to minimize this function? What do you have to do? Let's say f of x you want to minimize. What you are doing then? Hmm? This hopefully you have done quite often in your studies. Think of profit maximization or cost minimization. Actually, almost everything in economics is about identifying some aim and then minimizing or maximizing your aim, given, for example, your resources. What have you formally mathematically to do? Hmm? Nobody? Yeah, of course, I think introduction to business administration or microeconomics. I think especially in microeconomics, you have maximized and minimized lots of things. What have you mathematically done then? Can put it in the chat. Hmm? You're still there? Oops. Insert 1 or 0. I don't think this would be just try and error, but the second one is right. We take the derivative of our function and set it to 0. So in this case, f prime of x and set it to 0. And if we have two variables, a and b, then of course we have to take the derivative with respect to both variables simultaneously and setting these to 0. So what we are now doing is the derivative df with respect to our first variable a. So, and I don't know if you have often handled these summation sign, and therefore let's just write down how this function looks like, because it is just an abbreviation using this summation sign. So this would be then y1 minus a plus b x1 squared plus y2 minus a plus b x2 squared plus and so on until our last data point yn minus a plus b xn squared. And please keep in mind that y1, x1 are known, and also y2, x2, and so on. So what would be then the derivative of this first part here? df dA. Think of, if we just assume as an example, this would be maybe 1 minus, minus 1 minus a plus, let's say, 3b closing brackets twice and squaring. What is the different? What is the derivative of this function with respect to a? Hmm? Anybody? What is the derivative of f of x equals, let's say, x plus 2 squared? Well, let's take it that we have something similar. What we want to have, let's say 2 minus x. Then f prime is hmm, f of x equals x squared derivative. Oh, there it is. I haven't looked in the chat. Almost. F of x, 2x, yes. And the first one, think about it. 2, writing the exponent in front of the brackets. This is right. Then 2 minus x. And what we have missed then is that you have also to take the inner derivative, and this would be here your minus x. If f of x, so this would be 2x, and here 2 times 2 minus x, and here you have minus x. So what is the derivative of f of x is minus x. Derivative of f of x equals x. Hmm? or yes, -1. So from the inner derivative, we obtain an additional minus sign. So, and now we have everything together. We can go there in general. So this 2 just in front. So this would then mean 2 times y1 minus a plus b x1, and from this minus sign here, we obtain the inner derivative also minus here. And this, of course, we have to do for every part of our function. So plus -2 times yn minus a plus bxn. So, and this, of course, we can then put together again with our summation sign. And this then would mean we have at every part -2. This we can then put in front of our summation sign. So -2 times the sum, and now we have only in brackets our arrows and not squared anymore. So yi minus a plus b x I equals 1 to n, and this is 0. Well, and of course, we also have to take the derivative with respect to b. Then the outer derivative is, of course, the same. Now, here is our variable where we want to take the derivative. And this, again, would then mean we obtain a -2 times the sum y to n, again, yi minus a plus b xi. But now in front or behind every b within these brackets, we have x1, x2, and this has to be an x, xn. So as the inner part of our derivative, we obtain not only the minus, which is coming from this part, but we always, for every part of our term, we obtain also x1, x2, x3, and so on. So times xi. And this we have also to set to 0. These two have simultaneously to be set to 0. Well, and what we have now is not that complicated because we have no exponent here anymore. So here we have two linear dependencies between A and B. Still keep in mind, all yi and xi are known. These are just numbers. So what we now have then is two equations, linear and two variables. So this is just a linear system of two equations for two variables a and b. And this, of course, then we can directly solve. For example, you can solve the first one for a, depending on b, then feeding in this solution for a into the second one, then you are only left with your variable b, and then you can directly solve for b. So equation for two variables a and b, which can be easily solved. Well, of course, what you then see is if you're inserting all these numbers, then the solution looks a little bit complicated, but again, keep in mind all xi and yi are numbers. And these are then the formulas for our parameters a and b. Well, and if you look a little bit deeper inside this, then you see here, for example, the sum of xi and the sum of yi, and this is nothing else than n times the arithmetic mean of x and y. And then it can be shown that also our a has a direct dependence to the mean of y and the mean of x, and that in general the mean of both variables x and y is or has to lie on our regression line. This means also that the data point x bar, y bar has to lie on the regression line. Yeah. And b itself could then be calculated in this way, and I hope, because do you see this in this case? I hope I have done it right. So this is x bar times y bar, while you're taking here directly the mean of the multiplication of both variables. Well, what we also find is that b can be written as the covariance of x and y over x, while the covariance is just the multiplication of two deviations of x and y with respect to their means. Okay, and now we are more or less done. And what we want to do is using now these formulas in order to calculate our A and B. And this, of course, we want to do in Excel, and therefore I cut this, and this is a bit large. So, and if we look at this formula here, then we see, of course, we need the sum of x, we need the sum of y, we need the sum of x times y, and here at this point we need the sum of we need the sum of xi squared. And therefore, I just already put in here that we calculate here the multiplication of x and y, and here we calculate x squared. And this can be done taking 9 times 24, enter. And since we have here our formula, if you click in it, then you see that it is highlighted what you have done. And we can just copy this down here. And then we have always, for example, here, we're clicking in it here, 20 times 42, and this is 840. Also, we need the sum of x squared. So this squared, so 9 squared is 90, is 81, 11 squared is 121, and so on. And from all these numbers, we need the sums. So equals sum. Well, and now we go into our formula. Let's calculate b. So n times the sum of the multiplication minus sum of x, sum of y, divided by n times the summation of x bar minus, and now be careful, first summing up x and then squaring. So this is different from this. Here we first square every number of x and then we sum up, and here we first sum up all x and squaring done. So then we would have b equals n. N we need, n is the number of our data points. Let's write this down here. This is just 6, so we have 6 data points from 2008 to 2013. So this is our 6. So n, our 6 times, what did we have? Sum of x, y. So this would be our 2134 minus, oops, what happened there? Sum of x, sum of y. So 70 times 162, and then we have to divide it, this overall, to n times x squared minus sum of x in brackets squared. So what we then also need is that we have here brackets over opening brackets 6 times x sum of x squared 940 minus the sum of x 70 squared. So hopefully I did everything right. I think so. So B would be then 1.978. And then if we have this B, you could use, of course, this formula, or what you can also use is just this formula using that A equals y bar minus the slope B times x bar. So then we will have A equals y bar. Y bar is just 162 over 6 minus B, we have calculated, times x bar is 70 over 6. And then we have our regression line. So let's fit in this data here. I think this I easily can do. Oops. Is it working? Yep. And let's write down also the sums. This was 70. This was 162, 2134, and 940. And B was then again n times our 2134. So 6, 2134 minus, again we are looking it up, sum of x, sum of y. So 70 times 162 over 6x squared 940 minus 70 squared equals 978, and A was then y bar, so this would be y and x. Oh, I've written down it here. So 162 over 6, n equals 6 minus b 1978 times 70 over 6, and we had here 3.1919. 3.919. Well, of course, this we do not have always to do just always typing in this lengthy formulas within Excel. We of course have in behind these formulas, and this I show you too. So B is the slope of our regression line. So using just slope, or in German Steigung, and then our x values and our y values. For example, this formula you can then later on use when you're doing your time series analysis. Oops. This, I think I have. changed. What did I do? I have to take this one. Oh, the first one is Y, you see here. So I just interchanged the data points. So this one has to be C, this has to be C, and this has to be B, and this has to be B. Or this is the vertical axis. So we have the formula Achsenabschnitt. In German, again now the right one, Y and X. Enter. Or what you also can do is we are taking just the data points, plotting our data points, and then let's put it here. So this is Y and this is X. So Y was just sales volume, and these are our visits. And what you can do now is you can click into the data, then right click with your mouse, and then you see here trend line, and that you see it, we put it here. Then you can choose what kind of dependence you assume. We are assuming a linear dependence here, and we also want to see the numbers we are calculating, so showing formula, and what we get is our regression line, which is shown in our diagram, and here also let's put it a little bit larger. Take 16, and here we have also our 1.98 plus 3.92. So these are the different possibilities in order to get out these calculations. And on the next slide here, I showed you this one. Here we have our estimation, and well, what we have done then is, so to speak, with this line, we have minimized all the sum of all the errors squared. So if we look, for example, here on the area, well, and then I could, oops, say if I'm copying this, no, this is only the EI. This I don't want. I wanted to have this. Now I have it. Let's put this one. And oops, this back, so to speak. this one. Sorry. Here an even smaller one, roughly this one. This would be another one, and here this is almost vanishing because this point almost is lying on our regression line. And this one here. So, oops. So this line has minimized the area of the red squares. Well, if you think that if you would have a linear line with a lower slope, so just turn to the right, then of course all the areas of our red squares are changing, and these squares, the sum of these other squares would be then larger than the squares which we which we have now calculated via these two values for A and B, 1.98 and 3.92. Okay, and how can we now interpret our regression coefficients? Well, B is just the slope, and from this parameter B we can then interpret, well, if this parameter is, for example, in our case, roughly 2, then we know if we are increasing x by 2, then our y would increase by a factor of 4. And the regression coefficient A is then just the value for x equals 0, so it is the cut of the vertical axis. And if we would move this down here, then we are here at A roughly 3.91 or 92, sorry. Yeah, and now we are coming to the so-called correlation analysis, because of course this regression can be done for every data set. And then of course we can think of that our data points could lie very well in the neighborhood of our regression line, but also we can think of that maybe our data points are fluctuating very much around our fitted line. And then we want to have something like a measure, so to speak, how good is our regression. And this is then the so-called correlation analysis. Because in principle, this linear system we can always solve for A and B. And then we pose the question, well, how meaningful, how good is our regression? And this is done via the so-called correlation analysis. And this correlation analysis then gives us an idea about the strength or the goodness of our fit. And this was done in the beginning of the or this was, I think, around 1900 by two guys, Bravey Pearson, and they calculated a measure which lies between -1 and +1. -1 we can interpret as a totally antilinear dependence, and this correlation coefficient would be +1 if we are lying with our data exactly on an increasing line. Have you already heard from correlation analysis and the correlation coefficient maybe in your statistic course? Yes? Okay, great. Yeah, okay, then we will do it also that you remember this. So, for this, now, we want to, so to speak, directly want to have a measure of our shift of our data relating to the mean of our X and Y data points. I see this has to be an I and not a J. And remember variance? This was just defined as xi minus x bar squared, and this is the same as xi minus x bar times xi minus x bar. And what we are now just only interchanging is that we are, setting in this second part from variance, we are switching from x to y, and then we are coming to the so-called covariance. And also we have this factor 1 over n minus 1, and this means that this also, oh, I missed also squared here, that this covariance needs this factor n minus 1 in order to obtain a so-called unbiased estimator. But that's not that important. Think of you have a data set of 1,000 data points. So maybe you had a questionnaire and you were asking 1,000 people, then dividing by 1,000 or dividing by 999 doesn't really matter in, you have not that much difference. Well, so this would be then a measure for the spread of x with respect to x bar and y with respect to y bar. But then this would have just some number, but this number is hard to interpret. Because why? Well, we have a unit for x and we have a unit for y. Remember our example there, we have our x was the number of visits and y was measured in euros. So then we have the unit visits times euros. How should we interpret this? This is very hard. And also, if we measure this not in euros but in US dollar, then this number, this absolute number, will also change. And therefore, in order to interpret, we have to normalize it. And the normalized version then is called the correlation coefficient. And this one is normalized. So here we have more or less the covariance, and this is normalized by dividing just the square root of variance x and variance y. So this is the normalization. And if you keep this in mind and then putting just in the definition of covariance and variance, which we had here, then we of course also can directly compute this correlation coefficient from our data set. And here we have also this huge formula. And yeah, this correlation coefficient, there we can also show that this is of course also directly related to our regression line. Think of this regression line is of course fitted in that way that all the data points should be in a best way with respect to variance to the squared deviation to these regression lines. And with this we can show that this regression coefficient also equals the slope times variance x minus over variance y. And also what we can show is that this regression coefficient, we obtain it via taking all the data points lying on our regression line with respect to y bar over the total variance of y. And here we have the data points. So these are again points lying on the regression line, and these are again data points of y. Here, and then in general we can roughly say, and there you have to be a little bit careful because we are still only in a descriptive analysis, so we are not talking about causality, but in general you can keep in mind if your regression coefficient is in the neighborhood of 0, then more or less your data is fluctuating very much around your calculated regression line, and we could then for correlation coefficient between 0 and 0.2, we have almost no dependence, so there is not much explanatory fit in our regression. And if we are then in a neighborhood of 1, then we can say our data points are lying very closely on our regression line. Okay, and then if we are starting with our example later on, just think of this would be our data. What would be what would you think, where would be roughly our regression, not regression, our correlation coefficient? Let's start with the lower part here, lower left side, and the lower right side. What would you think is the correlation coefficient for this when all our data points are lying exactly on a line? Yeah, there's something in chat. Yeah, very close. Or here in this part, we can really say, well, if you look deeply in it, then these data points, they really should lie on a line, all data points lying on a line, and then we would have R equals really 1. And in this case here, again, yes, this would be an R0 because data points distributed totally symmetric. So, well, also by I, where should I put my regression line? This seems a plausible candidate, but since it is totally symmetric, this could be also a candidate, or even this one or this one. So there we really cannot distinguish what, with respect to the square distances, what would be the best fit for this. So then, of course, we would have a regression coefficient of 0, no dependence between x and y can be identified. Okay, and I think due to the time, then next time we will start, or yeah, this we can do. I think some minutes are left, because also quite often we are taking not r but r squared, and this is the so-called then coefficient of determination, and this one of course can also be interpreted as the correlation coefficient, which lies between -1 and 1. And if we are doing the square, then of course this number lies only within 0 and 1. And if we go back to this formula here, then, so to speak, we can interpret this coefficient of determination in a nice way, because this is, so to speak, the difference of our points estimated from the data, y hat star. So in order to, yeah, putting our regression line due to our data, let's say, for example, again, x and y, these are our data points. Then we could calculate the mean of our data set, and then we have the variance, the spread with respect to the mean. And now putting in let's take red. This is better. Uh, regression line, then overall our data points moving a little bit more in the neighborhood of this red line. So, and then, so to speak, the difference now between our turned line with respect to the mean y bar, so to speak, explains our data. And here then we have the square distance with respect with the calculated points on the regression line with respect to our arithmetic mean. And this is, so to speak, the explanation of our linear model we put in our data. And therefore, we then can graphically interpret the R squared that if, for example, we have here a number of 0.7, then we can, so to speak, interpret this number 0.7 that we are explaining with our linear dependence of y and x 70% of our regression, and of course then 100% minus this coefficient of determination. This would be then, yeah, our left unexplained part, because still in general our data will also still fluctuate around our regression line. And this is more or less the reason why we more often use R squared and not R, because of this graphical nice interpretation. But of course, we have to keep in mind squaring then means that we do not have anymore the information of plus or minus sign, because in the minus case we have this antilinear dependence. Okay, then on Wednesday we will do with our example also this correlation analysis, and then we will go to our economic data of unemployment and GDP for the United States and Germany. Okay, thank you very much for today.